double helical section of DNA, and you want to replicate it, then that's more nucleotides. So the first thing that's going to happen is that an enzyme, which we haven't talked about, is going to come in and melt a little piece of that chromosome. So if that's in the 5' direction, and that's the 3', and that's 3', 5', where can RNA primase, the enzyme, synthesize primers? It's only going to put one primer on each strand. So it'll do it wherever it can. So these are the first primers it will synthesize. So this is exactly like what we talked about in class.
Okay.
And these are going to be anti-parallel in orientation to the strands they're base paired with. So that's 3', 5'. Okay. So then maybe to make this easier to see, let's see, these double helices are totally base paired up to the replication fork where the strands split into two single-stranded. So that polymerase molecule will synthesize the blue for the 3' end until it runs into some sort of double-stranded DNA. In this case, it's where there's a separate enzyme. We haven't talked about helicase that sits right there at the replication fork and unwinds the DNA. It's the enzyme that actually does the melting. So that's maybe considered that to be step 1.
Okay.
Or at least time point 1. So if we look later on, just from this one replication bubble, the bubble will have gotten bigger because those helicase molecules are moving outwards. They're moving that direction. There's one sitting right there, moving in that direction, unzipping, kind of. The double helix, and there's also a helicase there moving that direction. So that's what makes the replication bubble get bigger. So we still have a lot of double-stranded DNA there. And we can zoom in again, and we're going to see that those original primers are still there. And now that there's a lot more single-stranded DNA that helicase has exposed, this is how far that newly synthesized piece of DNA had gotten in the original drawing up here. Right there. So that's that section of blue. And there's some newly synthesized DNA there. But because the replication forks have moved left and right, now that same molecule of DNA polymerase can keep synthesizing according to the base pairing that's been exposed here in that single-stranded region. So from those initial 2 primers, then what happens at the end of replication? When that top strand is entirely single-stranded, there's no more replication bubble anymore. Helicase just got to the ends of the chromosomes, and they're totally unzipped, totally melted. We still have those 2 initial primers, and now DNA polymerase has been able to synthesize all the way to the ends of the chromosome. And then I suppose that enzyme just literally flies off the ends of the chromosome. It's got no more single-stranded DNA as a template, so it's got nothing left to synthesize. It's done.
So that's synthesized from the 3' to the 5' direction, technically?
So those are the 5' ends of those primers.
Yeah, 5.
Yep. So it has just finished synthesizing the 3' ends of the new strands of the double helix. And this is where we got to at the end of class. I drew this in a different way, but I said, look, here's the problem, is that how do we synthesize the other half of that strand and the other half of that strand? So these 2 are the leading strands. because you use a single primer to start them, and then DNA synthesis proceeds without stopping until one of two things happens. In this case, until polymerase runs off the end of the chromosome. Or, in the real case in humans, when it runs into another replication bubble that's doing synthesis on the left or the right side. Is that okay so far?
Yes.
Okay. So, what happens next? At point 2, let's say, so here's time point 3, replication is about finished. So time point 2 doesn't quite look the way it really would in a cell. Yes, we've got an RNA primer there, and yes, polymerase is starting to synthesize DNA from its 3' end towards the ends of the chromosomes. So what else is going to happen at this time point? What else do we need to synthesize, for example, these little single-stranded bits of chromosome there and there?
The Okazaki fragment.
So these are going to be Okazaki fragments. And what do we need to initiate their synthesis? How do we start making more DNA there? Right, it always has to start with the 3' end of an RNA primer. And we wrote in that was the 5' end of the primer. And we know that because it's the 3' end of the primer that replication starts at and goes that direction. So where can we put a new primer to give a new 3' end for DNA polymerase to keep copying these single-stranded bits of the chromosome?
One of the smaller
So the primer is going to be synthesized on single-stranded DNA. So let's just say we put it there and there. RNA primase sort of, as far as I know anyway, RNA primase works at random. It finds single-stranded DNA, it just synthesizes nucleotides. So then we've got another 5' end, 3' end, 5' end, 3' end. So we've got two new primers that, again, RNA polymerase could come bind to the 3' ends, and then it would move that direction and that direction, filling in with newly synthesized DNA until it runs into the primer that was there before it. And then it stops. DNA polymerase stops, that is. So if we add those to this drawing, down at the bottom, what it looks like after replication's finished, there is that primer we just drew. And here is that primer, right there, and the DNA that got synthesized from them. But we still haven't finished completion of replication because that replication bubble, as replication proceeds, gets bigger and bigger and exposes more and more new single-stranded DNA. So all of this has to become single-stranded like it is here. So the very last step is RNA polymerase, or sorry, primase creates even more primers, and you get more synthesis in that direction. So from a replication origin, you can tell where the replication origin is too. Right? How would you know where the replication, if I covered up the top half of the screen, how would you know where the replication origin initially was? Approximately. So if I just drew this, each of those started with, oops. I'm colorblind, but not that colorblind. If you looked at the chromosomes after replication was complete, they would look like that, where the red are the primers and the blue is the newly synthesized DNA, and then there would be the original strand. So here's your semi-conservative replication. So that's what a chromosome looks like just after replication finishes, and where we're going to pick up class on Wednesday, because there's still some problems with these molecules. They're not really replicated chromosomes quite yet. So how would you know where the replication origin was?
For the longest strand, the broken strand.
It's going. What about the longest strand?
Look for the longest unbroken strand that.
So there's the longest unbroken strand. It's the leading strand. That was synthesis from one primer all the way until the end of the chromosome or another replication bubble. And there's a leading strand. And then there's a bunch of lagging strands, Okazaki fragments, there and there.
But that should indicate where the bubble.
Where was the bubble? How would you look at this and know where the replication origin started?
Where the Okazaki fragments start to begin their process, right?
Right, it's that fragment between where you have leading strands on one side and lagging strands on the other. Right, here's the leading strand, here's a bunch of lagging strands. There's same molecule, same strand of DNA, right? So there's a bunch of lagging strands over there, there's leading strand here, so the replication origin had to be in between, in that junction between the leading and the lagging strands. So each template strand is hybridized to a lagging, sorry, let me label this too. That's leading. That's lagging. So each original strand of DNA, the black ones, is hybridized to leading and lagging. Let's see. So single-stranded molecule of DNA, this is the problem with replicating telomeres. So let's see, that's the 5' end and the 3' end. So you can have primase build a primer there that base pairs with the DNA. 5' end, 3' end. And so then DNA polymerase can come along and bind to the 3' end of the primer and add in the new nucleotides up to the end of the chromosome, like we've discussed. So the question again was, how, at the very end, at the telomere of the chromosome, how would you get those 4 nucleotides synthesized? You'd have to have a 3' end of a primer there for DNA polymerase to come bind, and then fill in that direction, right? That would be the only way to synthesize those last 4 nucleotides on the end of the chromosome. But primase can't do that because primase needs DNA to base pair with the nucleotides to know which nucleotides to add to make the primer in the first place.
Essentially needs a starting line that
Yeah,
exists.
right, exactly. So in that case, what happens is those molecules of that end of the chromosome just doesn't get replicated because there's no place for RNA primase out here to put a primer that would allow that bit of the DNA to be synthesized. So every time a cell divides and every time the chromosomes replicate, they get a little bit shorter because that part of the chromosome hasn't been copied. And the next time, so then the chromosome gets to be that short. And then in the next cell division, the very end of the chromosome can't be replicated, so it gets a little bit shorter. And then the next cell division, it gets a little bit shorter. So cell division by cell division, the chromosomes get kind of chewed back from the ends a little bit. They get shorter and shorter, not significantly, but every cell division, a tiny bit of the chromosome doesn't get replicated.
You losing a portion of variation.
You just lose a bit of your chromosome. Fortunately, the ends of our chromosomes are telomere sequences, which are microsatellites. They're a type of satellite DNA sequence that doesn't code for any genes. Our telomeres are repeats of 6 nucleotides, TTAG3N, hundreds or thousands of repeats of this 6 base pair sequence over and over and over again at the ends of all of our chromosomes. And that means that when this end replication problem exists, yeah, our chromosomes get a little bit shorter, but all that's being destroyed is it's meaningless DNA. It's our telomeres. It's only after, so there are people that have medical conditions where their telomerase, the enzyme that creates the telomere sequences, doesn't work, have medical conditions because their cells don't maintain the lengths of their telomeres because that enzyme that does that is broken. We have a specific, consider it a polymerase. We have a specific enzyme that's a polymerase. All its job is, it's called telomerase.
It's to code for something that doesn't do anything.
All its job is to synthesize that DNA sequence at the ends of our chromosomes. That's its job. It knows it's supposed to grab onto the ends of chromosomes and put TTAG3, TTAG3, TTAG3. And if people don't have that enzyme, it doesn't work properly, then they're the individuals that are going to have the problem where replication, attrition, or the chewing back of the chromosomes at every cell division eventually does start chewing into genes. And that can cause medical issues. Although, having said that, I do have to say that telomerase is not something we want all of our cells to use. It's normal for our cells to age. Right? It's normal for us to age. What's bad when cells don't age? What's
Cancer.
that? That's cancer. When cells can divide and divide and divide and divide, and they don't senesce or get old, is another way to put it, or die, because cancer cells, a lot of cancer cells find ways to turn on telomerase to keep the telomeres in the cancerous cells long. And that's one of the ways that those cancer cells can grow and grow and grow and grow and grow and grow and never stop. Eventually, in a normal cell, the attrition of the chromosomes would kill the cells, but a lot of cancers, they use telomerase to keep themselves immortal.
So, I mean, not that it's relevant in this sense, but along the same line, as far as like cell death and aging goes, what about individuals who have the disorders where they don't age? I think it's not so much that they don't age, but they don't show the signs of physically getting older. Is it from
So could be telomerase based? I'm not sure.
Because they're the people who maintain like their kid appearance essentially.
It's the other ones.
They still get old, but they don't appear old anymore.
It's the progeria patients, the ones that are chronologically young but age really rapidly. That I don't remember specifically. I think those individuals sometimes have issues with, or have had issues with telomerase. We age faster than normal. I should look that up though, to make sure I'm not misleading you. Let's see. So that would be a use for OMIM. No, I don't want to donate though. So we look up progeria, and it's just showing me some genes that are involved in progeria which don't look familiar. So let's look up, that was looking up a disease. Let's look up telomerase, find out what diseases are associated with telomerase. Dyskeratosis congenita.
That's a fun word.
Telomere-related bone marrow failure. Yeah, so it looks like dyskeratosis. Let's see. Genetic disorder of defective tissue maintenance, impaired stem cell function, and cancer predisposition caused by short telomeres resulting from a defect in telomerase. So that's what no telomerase gets you. the one thing that telomerase defect gets you. So it didn't come up with anything about aging.
I'll have to. I'll
But
look it
yeah,
up.
explore a little bit more.
Because I saw a couple cases